Hello. We're ready for our first reaction in the carbonyl chemistry unit, and that first reaction is going to be the Wittig reaction. And the Wittig reaction was discovered by George Wittig, and he won the Nobel Prize in 1979. Nobel. A very unusual reaction. We're going to make a carbon-carbon bond. Not only that, it's going to be a carbon-carbon double bond. And um, the reaction is only takes 2 steps in the mechanism. Let's take a look at the reaction. Reaction A, the Wittig reaction. We're going to start out with a ketone or aldehyde, but let me do ketone first. Okay. The Wittig reagent looks a little bit strange. It's called an ylide, and it is 3 phenyl groups, and I'll draw that out in just a bit. Phosphorus, and then we have the piece that we're going to add to the carbonyl compound. And in this case, I'm going to do CH. So if you notice, the carbon right here has only 3 bonds. It does have a lone pair, and it's negative. And then the phosphorus is going to be positive. That's it. That is called the Wittig reagent. And we'll have time. I'll show you how to make the Wittig reagent because maybe in a synthesis, your professor will say, well, you can't buy this. How do you make this? And I'll show you that also. What are we going to do? You're going to find this carbon, the carbon of the carbonyl, and all you got to do is take this piece, and get a piece of paper, this piece right there, okay, the CH3, and stick it where that oxygen is. Okay, we're going to make an alkene, and we're going to make an alkene, and we have a choice whether to make the cis or trans, and typically you're going to make the more stable trans alkene. When you draw the product, just go ahead and draw the double bond, but don't draw that oxygen. Pretend that that carbon is now this carbon, and we have an H and a CH3. To make it trans, we'll put the CH3 here, on the less crowded side, and we'll put the H here. You see how literally that this part of the molecule, those atoms are exactly those atoms right there. Okay. This is a very popular reaction in a synthesis problem on an exam because what if you're given this? And the professor may ask you what combination of aldehyde or ketone and Wittig reagent could you use to make this? Well, you just have to pretend that, oh, well, either I started out with that ketone, okay, pretend there's an oxygen, or I started out with that, in this case it would be aldehyde, okay. So there are 2 ways actually to make this via the Wittig reaction. Looking back at our starter material, the ketone part was the bottom half, but it could have easily been switched, right? We'll do a couple more examples. Oh, and we'll also do the mechanism. It's a really interesting mechanism. The vinegar reagent, though, is what's called an ylide, and technically phosphorus ylide, and that's when you have this plus minus next to each other. What should we do next? Let's do another example actually. Let me give you a ketone. And I'm going to give you another form of the Wittig the Wittig reagent. Another form of the Wittig reagent could be when you have a double bond between the phosphorus and carbon. You know how we got that? By just doing resonance. By pushing these two electrons down, that will make this phosphorus neutral and this carbon also neutral. Okay, by just pushing these two electrons down. So the phosphorus ylide could also look like this. And what groups do I want to give us? Let me try this one. Do you see what that might possibly give us? If you want to give it a shot, go ahead and pause the video and draw the product here. Use this as a template. Okay. Think about what we added, what we replaced. Right. Don't worry about the mechanism, but try to use this as a template and see if you could fit what you know to these two starter materials. Pause the video. Okay. What I'm going to do is I'm going to draw the ketone part, but don't draw the oxygen. And now this carbon is this carbon, and I have two ethyl groups, CH2, CH3, two of them. And maybe the best way to draw them like this. Right? Doesn't matter. There's no cis and trans, as you know, for this molecule because, well, this carbon has two of the same groups, and also this carbon has two of the same groups. Right, so that is your, what do you call it? That is your product. What's another way to make this? Why don't we play that game right now? Instead of using this ketone and this ylide, can you tell that maybe we could have used a ketone that looked like that? And the ylide part would provide us this piece right here. And this chord. Okay. I want to start out with this ketone. And I am drawing it so it looks the same carbon skeleton as we have in the product. But practice. What would your Wittig reagent look like? Your Wittig reagent would look like this. Now we could use the double bond version, this resonance contributor format, or we could use the plus minus. I was taught predominantly using this form of the ylide, so I'm going to do the same thing. Well, pH3, this is plus, and this is minus. I made that bond on purpose really long, because what's going to happen here? This oxygen now is going to be replaced with this chunk right here on the left. You see now that an alkene can typically be made via a Wittig reagent or Wittig reaction two ways, two different combinations. Okay. I'm going to show you the mechanism, and then we'll go over actually how we make this Wittig reagent. In the mechanism, before we draw anything down here, what's happening? We predict. We use the concept of opposites attract to at least figure out, well, how did we get that carbon right there attached to this dot? Well, there you go. This carbon is partial positive, right? So you would think that this negatively charged carbon would be attracted to this partial positively charged carbon. Okay? And we have lone pairs here. Maybe those lone pairs are attracted, right? The electron-rich oxygen is attracted to the electron-poor phosphorus. You could do the same. Actually, I don't draw the mechanism using this Wittig reagent normally. We're going to go ahead and draw the reaction with this form of the Wittig reagent. Let's do the mechanism for the first reaction that we saw. It's just two steps. I'm going to draw this bond a little bit longer than normal, and I'm going to make sure I have that dot. and you want to line up. Opposites attract. So you just have to be kind of careful and make sure you line up the carbon that's negatively charged, and the phosphorus, we're going to line it up here, right? So it's facing the oxygen. So when these two molecules collide in this orientation, the reaction would most likely happen, and we have this movement. Now, I have to warn you that many websites and textbooks say that you're going to push the pi bond up to the oxygen to make it negatively charged. But there are other, it's debatable. It's not conclusive. There are other groups that say, well, no, at the same time, the pi bond is going to be attracted to this phosphorus. And that's the way I was taught, and I'm going to teach it that way. Concerted. This is called a concerted mechanism, because these two bonds that are being formed essentially at the same time, right? That at the same time, or concerted. Can you predict what my errors are going to give me? My errors are giving me this. I'm going to draw this methyl group out of the way, and still have this bond to oxygen, but now it's a single bond. We have a bond to phosphorus, that's this arrow up here. Bond to carbon. When I draw the mechanism, I normally do draw the letters, not use line drawing on this part of the molecule. And the first arrow told me that I made this bond right here. And we have our two groups off of that carbon. Everything is neutral. Wait, is everything neutral? Oh, I forgot the phenyl groups. I know I haven't told you what phenyl is. That'll be coming up. I just want to make sure that everything is neutral and everything is neutral. So that's your first intermediate. And then the product is going to be made in this last step. Now, I like to call this collapse of the four-membered ring. And the way that I would collapse it is, well, think about what we need to make. We need to make a double bond between the dot and the carbon from the Wittig reagent. So the dot is here. The Wittig reagent is this part on the right, and we need to make a double bond there. But to make that double bond, I would think of it this way. You're going to weaken this bond and make the double bond here to make an oxygen-phosphorus double bond. That actually is a very strong bond, and that's what's called the main driving force of this reaction, to make that strong oxygen-phosphorus double bond. And then this collapse right there. I did find some sources where the arrows were a little bit reversed, where the double bond here was made with this bond on the right. And then what will happen? This bond collapses to make the double bond between the two carbons. My preference is this way. Have the carbon-oxygen bond be attracted to be in between the oxygen-phosphorus bond. But if any of my students do it the other way, right? If any of my students do it this way, where we take this bond and put it up here, and then have this bond collapse down, I want to count it wrong. What do we make here? Well, hopefully it's obvious that we made this molecule here, right? And then what else do we make? We are going to make sure that we rotate it so the carbon-carbon double bond is a trans double bond. And we have the double bond, we have the methyl group, and there's an H. And I'll draw the H. You don't have to, but those are your two products. Here is that the phosphorus oxygen double bond is strong. Okay, it's very stable. Way to describe it. And you want to form stable products, right? Equilibrium will favor the more stable products. So that's your driving force. excellent reaction. I mean, uh, there's no doubt why Wittig got the Nobel Prize for this. Made a carbon-carbon bond. How many times have we been able to do that? Um, very rarely in organic 1, right? And not much yet in this organic 2 course. Okay? Not only that, it's a double bond. So think about what kind of questions your professor may ask. They may ask you, well, fill in the reagent, or even uh, more practical, draw me a synthesis using the Wittig reaction to make this alkene. Okay? Let me show you how to make the Wittig reagent, because maybe you don't have this as one of your starting materials. Maybe you have to make it, and we're going to make it from an alkyl halide. And the Wittig reagent we're going to make is the one that we just used. Okay? So this is a practical synthesis because, yeah, maybe I did want to make this molecule here, and maybe I had the ketone, but I don't have the Wittig reagent. That's my target. So the target is this dude right here. And yeah, you've been very patient. What does this 3-phenyl groups look like? Phenyl is another name for benzene when it's a substituent. And we're going to start out with the phosphorus with 3-phenyl groups. And I'm going to draw them out here. But after this, for the rest of the mechanism, I'm just going to draw the abbreviation or the condensed structure. So this is a triphenylphosphine, very popular reagent for other reactions as well. Triphenylphosphine, 3-phenyl groups. The first thing is we're going to attack a alkyl halide. What alkyl halide? Very easy. Just put a bromine. There's 2 things actually. Because now if I cover up this stuff on the left side, the carbon's missing 2 bonds. Right? It only has 2 bonds right now. You're going to add a hydrogen and an alkyl halide. So you're going to add a hydrogen and a bromine. It's definitely 2 carbons. So tell me whether this is correct. See, I had to add a bromine and also another hydrogen. So this carbon has 2 hydrogens. This carbon only has 1 hydrogen. So I'll show you later how do we remove that hydrogen to get the Wittig reagent. But those are my carbons, and these are the 2 carbons corresponding to the Wittig reagent. Okay. I'll draw the mechanism as well, actually. This is a synthesis / mechanism. We'll just take it out. And now I'm going to use the condensed structure for phenyl. We have 3 phenyl groups, a P that's now attached to this dot that's attached to this methyl group. You see how we're getting close? This phosphorus is now positive, but this carbon is still neutral. Right? It still has 2 hydrogens. This only has 1, so we're going to have to use a strong base. And the base that many people use is called N-butyl lithium. And you're allowed to use the abbreviation N-butyl lithium. But what is that? That is the same as a butyl group, but next to lithium. We haven't talked a lot about molecules that have this carbon-metal bond. That is coming up. Another way you could think about this, there are shades of gray, and some people think this is a covalent bond. Other people think that it's more ionic, and that should not be a 3. That should be a 2. And Right? Either way, the main point is it's a very strong base. Right? You know that this is a strong base, and this is another way to draw what I drew down here. Okay, so yeah, should I do the mechanism? I'll just do the mechanism. Let me draw N-butyl lithium again here. Base grabs a proton, and we make the anion. That's where we get the C minus from the second step. And how are we going to draw this? We can draw it several different ways. Again, I like to draw the carbon connected to the phosphorus. And you could draw bonds, or you could just draw the condensed structure. You don't have to draw the lone pair if you're not going to be using it in a mechanism. Okay? I mean, we're done. This is our target. Our target's up here. So, at home, what can you do? You can figure out how to make this Wittig reagent, how to make this Wittig reagent. Let me just show you, for those of you who are still curious, like, could you show us how we get that second form? All you have to do is do a resonance. So draw this mechanism arrow, and then you draw this resonance arrow, and our result, our contributor, is this. I believe that's all I want to talk about in terms of the Wittig reaction. I'll leave you with one problem. We worked with two ketones. Let's do an aldehyde. A very simple aldehyde, but sometimes simple things, simple molecules can trip people up. And let me give you a Wittig reagent. Now, let me draw line structures. So there's one group, and then the other group is product. My suggestion is draw this out so you see the double bond, the carbon-oxygen double bond. Okay, that is the Wittig reaction. Done. With that, a lot of good questions that a professor could ask on an exam. But there are other ways to make a carbon-carbon bond, and we're going to look at other carbon nucleophiles and how they react with carbonyl groups. Essentially, that's what we had. We had the Wittig reagent interact with the carbonyl group through the carbon of the carbonyl. Let me show you reaction B. These are going to be fairly quick and simple. We're going to do a cyanide, and we're going to do addition of cyanide. Let's take cyclic ketone, and we're going to do it this way. We're going to first attack with cyanide, and then protonate with acid. Oh, there you go. Sorry about that. With your dot, we'll go through the mechanism, but to get the product as quickly as possible, pretend that your cyanide, well, not pretend, visualize it attacking this carbon, pushing this pi bond up to the oxygen to make it an O minus, then protonating it. This is called a cyanohydrin. Cyano for the cyanide group, or now it's a nitrile group. Cyano group, nitrile group, same thing. Cyanohydrin. One word. And you've heard of halohydrin, where you have OH and a Br, or OH and a Cl. This is not halohydrin, this is cyanohydrin. Your mechanism. Fairly simple. We don't have acid, so we're not going to protonate the oxygen. Right, that's what we have on the cartoon. Here you could have protonated the oxygen if we were under acidic conditions, but we're not under acidic conditions. All we do have is a salt, and that salt separates the cyanide, and we attack that carbon, pick up the pi bond, like this, and we have CO. The next step and the final step is with acid. Out of ink, and running out of ink and running out of time. Now, it doesn't matter here because the carbon is achiral, but you know this double bond is flat, and the cyanide can come from the top or the bottom. So you could have stereochemistry if this carbon was chiral. The last reaction is a reaction that you've seen already, but I'm going to add it here again. We saw this in organic 1. Maybe I won't give it a notation. I'm just going to say remember or recall. What's another carbon nucleophile that we're familiar with? Oh, no, let's not say recall. Let's give it reaction C. We're going to use something that's very familiar from organic chemistry 1, but we're going to use it in a different way. And that is the addition of a triple bond anion, which we've done before, right? So we'll call this alkynyl anion. Let's do an aldehyde. And the alkynyl anion I want to use is just a very simple one. Yeah. You know how to make this, right? From the terminal alkyne. You could just use NaNH2 to deprotonate. But we know that there's going to be an O minus here. And so we're going to make sure we protonate that oxygen. Now, maybe we'll get a mixture. Maybe we'll get a chiral carbon. Because again, that carbonyl is flat, and that guy can come in and attack this dot from the front or the back. Yeah. There's your H. Maybe attack from the front first. You're gonna have to practice this, make it look good. And then it pushed the oxygen to the back. And that oxygen got protonated with hydronium. Now this alkynyl anion can attack from the back. If it attacks from the back, it's going to push the oxygen to the front. So that's the strategy here. Comes from the back. And when that alkynyl anion comes from the back, it pushed the oxygen to the front. O minus, but then that O minus got protonated. I don't know if there's any special name for this, like we had for the cyanohydrin. This is just an alkyne alcohol. Why don't we go with that? Alkyne alcohol. We're not going to name this. I believe the hydroxyl group has priority, but don't hold that to me. What's more important in my mind is that you understand the products that you make, and that is racemic. And also, well, if I give you the targets, do you know what combination of aldehyde or ketone and alkyne anion you have to use to make it? Great. Got done with 3 reactions. The major one, as you can tell, is the Wittig reaction. Go ahead and make sure you study that very well.